Good morning, friends. I welcome you to the second session of mine on the molecular spectroscopy. In the first session, we discussed about what is spectroscopy, what are the different types of regions of electromagnetic spectrum, and what are the different types of spectra. And we learned that depending upon the energy associated with different types of electromagnetic radiations, we have different types of interactions occurring between the matter and electromagnetic radiation and giving rise to different spectroscopic techniques. And each spectroscopic technique gives certain information regarding the structure of a molecule. So, in continuation of that, today we will be discussing about the microwave spectroscopy or rotational spectroscopy of diatomic molecules. We are considering simple diatomic molecules, and also the diatomic molecules are considered to be as rigid rotors. So let us try to understand, let us try to know what are the different terms that we come across in the microwave spectroscopy of simple diatomic molecules. So we learned that molecules possess different types of motion, namely rotational, vibrational, and electronic motion. So in rotational motion, the molecules rotate. If you consider this as a diatomic molecule and the center of gravity lies near to the larger atom, so the molecule can rotate in this direction along the internuclear axis, or it can also rotate about the axis, running, passing through the center and perpendicular to the internuclear axis like this. This is another type of rotation. It can also rotate in this way. So there are three different types of rotational motion. Simultaneously, the molecule will also undergo vibrational motion. During the vibrational motion, the atoms move to and fro about the equilibrium position. So during vibrational motion, the bond length changes, it increases and decreases. Therefore, we call the bond length as equilibrium internuclear distance. And also, there will be electronic motion. So, in a molecule, all these motions will be taking place simultaneously. So, while deriving expression for moment of inertia of diatomic molecule, or while studying microwave spectroscopy of diatomic molecules, we assume this molecule to be behaving as a rigid rotor in the sense, though along with the rotation there is a vibration taking place, we assume the bond length to remain constant. So that is called as a rigid rotor. So rigid rotor is a molecule in which during its motion bond length is assumed to remain constant. Then what is center of gravity? So I have shown here a simple atomic molecule and a point as a center of gravity. So what is center of gravity? So center of gravity is a point at which the moments of the two atoms are equal. What's moment? Moment is nothing product of the mass and the distance of the center of the atom to the center of gravity. So that is the meaning of moment. So center of gravity is a point at which moments of the two atoms in a diatomic molecule are equal. Then the third term that we come across is moment of inertia denoted by capital I. We are all familiar with the term inertia. What is inertia in physics? We say inertia is the tendency of a body to be in the state of rest or in the state of motion unless it is acted upon by an external force. So, like that, molecules possess moment of inertia. So, what is this moment of inertia? So, if I consider this atomic molecule, moment of inertia of this molecule is the tendency of this molecule to resist change in its rotational velocity upon application of an external force or time. So, moment of inertia of this diatomic molecule is the tendency of this molecule to resist change in its rotational velocity by the application of a force or time. That is the meaning of moment of inertia. So, once we are familiar with these terms, Now, our point is to know which type of molecules can be studied by microwave spectroscopy, or what is the condition for microwave activity of a molecule. So, any molecule to be studied by microwave spectroscopy should possess a permanent dipole moment. Permanent dipole moment. So, only such molecules possessing permanent dipole moment can be studied by microwave spectroscopy. So, what is meant by dipole moment? So, if you consider a molecule like HCl, a simple homonuclear diatomic molecule, HCl, and we know the bond between hydrogen and chlorine is a covalent bond. One electron of hydrogen and one unpaired electron and chlorine are shared. So, a covalent bond is formed by mutual contribution and sharing of electrons. So, here HCl bond is formed by mutual contribution and sharing. The electron pair, the shared pair of electrons, lies close towards chlorine because chlorine is more electronegative than hydrogen. Hence, this covalent bond is not 100% covalent, but it implies a partial positive charge. The bonded pair of electron, which is expected to be exact at the center, is not at the center, but it is lying close towards chlorine because of higher electronegativity of chlorine. Hence, the hydrogen atom acquires a partial positive charge and chlorine acquires a partial negative charge, leading to polar nature of covalent bond, which is called polar covalent bond. Or with other terms, this covalent bond has a certain degree of ionic character. So whenever a polar covalent bonds, the bond will possess a dipole moment denoted by mu, and this dipole moment is product of the magnitude of charge and distance between the charges. So here delta, I am not doing delta plus or delta minus because both these are equal in magnitude but opposite in sign. So dipole moment is the product of magnitude of charge and distance between the charges. So HCl molecule possesses dipole moment. So HCl can be studied by microwave spectroscopy. Like that, any hydrogen halides, it could be hydrogen bromide or hydrogen iodide or hydrogen fluoride, they can be studied by microwave spectroscopy. So if you consider polyatomic molecules like water, ammonia, even these molecules possess permanent dipole moment. Therefore, these molecules can be studied by microwave spectroscopy. But if you consider homonuclear diatomic molecules like N2, O2, CO2, linear molecules like carbon dioxide, or regular tetrahedral molecules like tetrachloromethane or carbon tetrachloride, all these molecules are non-polar. Why? They do not possess permanent dipole moment. So, such molecules cannot be studied by microwave spectroscopy. So, why these nitrogen molecule, homonuclear diatomic molecules do not possess permanent dipole moment? Because it's a homonuclear diatomic molecule, atoms are same, electronegativity is same, so the bonded pair of electrons will lie exactly at the center or at equal distance from both the atoms. Therefore, these bonds are pure covalent bonds, hence no dipole moment. So mu is 0, they are non-polar. But on the contrary, if you consider carbon dioxide molecule, where there are two carbon-oxygen bonds which are polar covalent, but still carbon dioxide is non-polar because the two dipoles due to carbon-oxygen bonds are exactly opposite to each other and they are equal in magnitude. Therefore, these two dipole vectors cancel and net dipole moment becomes 0. Therefore, carbon dioxide is non-polar, which cannot be studied by microwave spectroscopy. Similarly, if we consider tetrachloromethane or carbon tetrachloride, there are 4 carbon chlorine polar covalent bonds. So there are 4 dipoles oriented at an angle of 109 degrees 28 minutes to each other. Since they are at the same angle, the orientation of these 4 dipoles are at an angle of 109 degrees 28 minutes. So since it is a regular tetrahedral structure, the vectorial sum of these 4 dipoles becomes 0. Therefore, net dipole moment of carbon tetrachloride is 0, it's not polar. So even carbon tetrachloride cannot be studied by microwave spectroscopy. But if we just change, if we just replace one of these fluorine atoms by hydrogen atom, then there are 4 vectors, different dipole vectors. Here, carbon is more electronegative than hydrogen. So we have 3 dipole vectors due to CCl bonds. 4th one is due to CH bond. So since they are in different directions, and the molecule possesses net dipole moment. Hence, the molecule becomes chloroform is a polar molecule which can be studied by microwave spectroscopy. So, what we learned is that only polar molecules can be studied by microwave spectroscopy. So, the condition for microwave activity of molecule is that the molecule should possess permanent dipole moment. Right. So, with this background, now let us focus our discussion on deriving the expression for moment of inertia of diatomic molecules. We will be studying about the microwave spectroscopy of diatomic molecules behaving as rotors. So, in order to derive the expression for moment of inertia, let us consider a diatomic molecules, diatomic molecule AB, where mass of the atom A is m1 and the mass of atom B is m2, and let this point be the center of gravity, and the internuclear distance R bond length of this AB molecule is taken as R naught, and let R1 be the distance of center of gravity to the center of atom A, and let R2 be the distance between the center of the atom B and center of gravity. So, from the definition of center of gravity, we can write m1 r1 is equal to m2 r2, where m1 is the moment of atom A and m2 r2 is the moment of atom B. And also from the diagram, r0 is equal to r1 plus r2. And moment of inertia is given by the expression I is equal to m1 r1 square plus m2 r2 square. Because in physics we have learned moment of inertia is given by the summation of m r square, where m is mass and r is the distance from the center. So here from the definition of moment of inertia, we can write the expression for moment of inertia of this molecule as m1, because the diatomic molecule, moment of inertia of atom A is m1r1 square, moment of inertia B is m2r2 square, and this also can be written as m1r1 r1 plus m2r2 r2. The r1 square is written as r1 r1. R2 square is written as R2 R2. So this is the equation. But from the definition of center of gravity, we have m1 r1 is equal to m2 r2. Therefore, equation 3 can be written
1 and 2. From equation 1, equation 3 can be written as, from equation 1, equation 3 can be written as M2 R2 R1 plus I have replaced M1 R1 by M2 R2 and M2 R2 can be replaced by M1 R1 R2 and R1 R2 are common in both expressions. Therefore, we have I is equal to R1 into R2 plus M1 plus M2. This is equation 4 for moment of inertia. But from equation 2, equation 1 can be written as M1 R1 is equal to M2 R2 and M1 R1 can be written as M1 into R0 minus R2. Since R0 is equal to R1 plus R2, R1 will be equal to R0 minus R2. Therefore, we have M2 R2 is equal to M1 R0 minus M2 R2. So if you rearrange this, we have
M1.
M1 R2. So we have M1 R2 plus M2 R2 is equal to M1 R0. Or we have this R2 being common, R2 into M1 plus M2 is equal to M1 R0. Or R2 is equal to M1 R0 divided by M1 plus M2. This is equation 5. Similarly, we can write expression for R1 as M2 R0 divided by M1 plus M2. So now, using these equations 5 and 6, equation 4 can be written as, we substitute equation 5 and 6, substituting equation 5 and 6 in equation 4, we have I is equal to R1 M2 R0 divided by M1 plus M2 into R2 is M1 R0 divided by M1 plus M2 into M1 plus M2. So we have this as M1 M2 R0 square divided by M1 plus M2. So this can be rearranged as M1 M2 divided by M1 plus M2 into R0 square. This M1 M2 M1 plus M2 is replaced by mu, where mu is called reduced mass. So reduced mass of a diatomic molecule is nothing but the ratio of product of masses to the sum of atomic masses. So this is the expression for moment of inertia, where I stands for moment of inertia, mu is reduced mass, and R0 is equilibrium internuclear distance. So this using this expression, we shall solve some problems. So this is the important expression that one should be able to derive from. So based on this, we can calculate some problems. Calculate reduced mass of hydrogen iodide given atomic masses of hydrogen and iodine. One point 673 in 10 power minus 27 kilograms and 2.106 into 10 to the power minus 25 kilograms respectively. This is the problem. So we have to calculate reduced mass. We know the expression for reduced mass, that mu is equal to m1 m2 divided by m1 plus m2. And should not get confused, the atomic mass of hydrogen and iodine are given in terms of kilograms. So all of us are familiar that atomic mass of hydrogen is 1. That 1 is what? That's 1.008 atomic mass units. But here it is in terms of kilograms. So be careful, do not get carried away. So 1 atomic mass unit is 1.66 into 10 to the power minus 27 kilograms. So please remember that. So these are the masses of hydrogen iodine. So we have 1.673 into 10 to the power minus 27 kilograms into 2.106 into 10 to the power minus 25 kilograms divided by 1.673 into 10 to the power minus 27 kg plus 2.106 into 10 to the power minus 25 kg. So when we simplify this, we get answer as 1.66 into 10 to the power minus 27 kilograms. Look at this kg. This kg gets cancelled. Ultimately, the SI unit of reduced mass is kilograms. Now, similarly, we shall have one more problem where we'll be calculating the moment of inertia. So, in problem 2, atomic mass of hydrogen and chlorine are 1.673 into 10 to the power minus 27 kilograms and 58.06 into 10 to the power minus 27 kilograms respectively. Calculate moment of inertia of HCl. Bond length of HCl is equal to 129 picometers. So 1 picometer is 10 to the power minus 4 meters. So first what we should do is, we know I is equal to mu r square and mu is equal to m1 m2 divided by m1 plus m2. So the reduced mass of HCl would be equal to 1.673 into 10 to the power minus 27 kg into 58.06 0.06 into 10 to the power minus 27 kilograms. Again, do not get confused. Atomic mass of chlorine is 35.5 U, but here it is in terms of kilograms, divided by 1.673 into 10 to the power minus 27 plus 58.06 into 10 to the power minus 27 kilograms. So if you simplify this, you get reduced mass of hydrogen chloride as 1.63 into 10 to the power minus 27 kilograms. Further, so moment of inertia is equal to mu naught square r square. So we have mu as 1.63 into 10 to the power minus 27 kilograms, and r is 129 picometers. So I write it 129 into 10 to the power minus 12 meters whole square. So upon simplification, we get this as 2.7 into 10 to the power minus 47 kilogram meter square. So SI unit of moment of inertia is a kilogram meter square. So let me stop here. We'll continue in the next session. Thank you.